Okay, children, so this is going to be our instructional video for lesson 6-1/2. We're going to be talking about inverses of functions, and we're going to talk about how we go about that algebraically and geometrically. So first of all, how do we calculate the inverse of a function? How do we express a function's inverse with proper notation? How can we use composition of functions to determine if functions really are inverses or not? And how can we identify functional inverses based on graphical symmetry and their domain and range? Okay, so first let's talk about what a inverse even is. Okay, so the four arithmetical operations, you've got addition, subtraction, multiplication, and division. Okay, so the inverse of adding, obviously, that's subtracting, and vice versa. Then you've got the inverse of multiplication is division, and the opposite there is also true. Okay, so when we're saying the inverse of a function, so the first thing that should come to mind, and you should kind of remember this from geometry last year. So let's say I had x equals the sine of y. Okay, so x equals the sine of y. That's what I've got right here. Well, typically we want things written out as y equals f of x, right? We want to express y as a function of x. And right now we don't have that. So what I'm getting at is y is not by itself. Y is not a function of x right now. Right now, x is a function of y. And as far as we're concerned, that's no bueno. Okay, so what would we do? So I've got sine y equals x. What would we have to do to get y by itself? Well, if you remember from geometry last year, basically we need to get rid of the sine. We need to get rid of sine. Well, back over here to the inverses of arithmetical operations. What was the inverse? What was the inverse of sine? Well, the inverse of sine was arc sine. Okay, and another way to write that was with a sine and a little -1 like that. Okay, so basically that's what we're going to have to do. Okay, so we're going to take the arc sine. We're going to take the arc sine of both sides. And it's algebra. So what I do to one side, I do the other. So arc sine, sine are inverses. They quote unquote cancel. And again, what I do to one side, I do the other. And y is now effectively by itself and is equal to the arc sine of x. Okay, so that just reaffirms what we were saying here. Sine and arc sine are in fact inverses. Okay, so that was the inverse of a function. And here we've got a graph of one, right? So in blue, you can clearly see this is what the graph of y equals sine of x looks like. Okay, here in blue. And in purple, this is y equals arc sine of x. Okay, and if you notice, there's a weird kind of a symmetry. There's a weird kind of a symmetry between them. Okay, and that becomes very apparent if I do basically this, and let's see how crappy I can draw this. So if I basically do this, right, you can see a symmetry there. And this red line that I do represents y equals x. Okay, that's going to be important here in a little bit. So let's talk more about what an inverse is. Okay, so we've got another function in front of us. And I'll use green because that's a little bit less boring. So f of x equals x squared. Okay, so question 1 is asking what's its domain and range. So for its domain and range, here's my x, here's my f of x, or my x and y. What is this graph going to look like exactly? Well, if you don't remember from Algebra 1, this is just going to be your basic parabola. Okay, your basic parabola. So let's answer the first part. What's its domain? Well, there's nothing. There's absolutely nothing restricting x. So our domain would just be x such that x is a real number. That's how we would say it with set notation. And if we're using parenthetical interval notation, we would just say negative infinity to positive infinity, right? There's no limit on what x can be. Now, what if we look at its range? Well, its range is going to be a little bit different, right? Its range is right here at 0, and it goes on and on and on and on and on to positive infinity. Okay, so its range would be y such that y is also a real number. But we do have a range restriction, and our range restriction would be that y is greater than or equal to 0. Okay, and parenthetical notation would look like this. So we would include 0 with the square bracket, and we would go on and on and on to positive infinity. Okay, so that's our range. Now let's talk about its inverse. Well, what is the inverse of x squared? So if I've got x squared, well, what is the inverse, right? So going back to what we did here with sine and arcsine, right here. Okay, so if I've got x squared, what's the inverse? What's the inverse of squaring something? Well, the inverse of squaring something would be the square root of something, right? So basically, the inverse of this function here, the inverse of f of x, would be plus or minus the square root of x. Okay, and when we start talking about square root and quadratic functions, we'll talk a little bit more about why it has to be plus or minus. Okay, but you don't need to worry about that right now. So what that's going to look like, if you throw this into Desmos, is basically like a sideways parabola. Putting my art skills not to good use. Let's see if I can draw that a little better. Nope, still looks bad. There we go. That's better. Okay, so what I've got is like a sideways parabola. Okay, so the inverse, so there's that little -1 again that we saw with arcsine, right? That little -1, that represents inverse. Okay, and here we're seeing it again. Okay, so the inverse of f in this case would be plus or minus the square root of x. Okay, and geometrically speaking, let's talk about that because that is very, very important. Geometrically speaking, and let me decide what color I want to use here. I'll go ahead and use red because I did last time. Well, why is that important? Well, you notice there's like a symmetry here. Okay, if I say that this red line represents y equals x, just like this, okay, this red line kind of splits these two. There's a symmetry between the parabola, the green parabola, and the blue sideways parabola. Okay, this is how we can tell two functions are in fact inverses. Okay, is this right here. If a symmetry exists about y equals x, if there's a symmetry about y equals x, then the two functions are inverses. Okay, that is very important. Okay, that's how we can tell. Other than just the obvious, well, what was the inverse of x squared? Well, the square root of x, right? So that seemed relatively obvious. Okay, so that's how we geometrically can prove two functions are inverses. Okay, and again, if we back up, okay, so arcsine of x is here in purple, and sine of x is in blue. And obviously there is a very, very clear symmetry about the line y equals x. Okay? So let's get into the actual algebra behind all of this. And let's talk about all this notation. So we've got 4 examples here. We've got 4 examples here that we want to look at and further discuss what this all means and what the point of it all is. Okay? So let's look at the first function. So we're here on number 1. So f of x equals negative 3x plus 8. Okay, and I want to know what's the inverse of x, or not of x, of f. Okay, and the proper way to say the inverse of f is just like how we did. So if this is f of x, our inverse would be f negative 1 of x. Just like the inverse of sine, right? The inverse of sine is arc sine. Okay, that little minus 1, that means it's the inverse function. Okay, so back over here, that notation still holds true. So what we're really asking is, if f of x is negative 3x plus 8, what is f to the minus 1 of x, or the inverse of f of x? Okay, so the way that we do that, the simplest way to go about this is kind of going back to our little trig example. Okay, so if I wanted to know the inverse of sine, or sorry, if I had f of x equals sine x, right, and I wanted to know, well, what is the inverse of f of x, what I would do is basically what I've got here. I would do the old flipperoo. So I would go back to 8th grade and start calling f of x just y. Okay, next thing I'm going to do, I'm going to rewrite such that our variables are flipped. Okay, so I'm going to do what I have here circled in white. I'm basically going to flip and say that x equals sine of y. Then I'm just going to solve for y. Okay, and again, going back to what we did, in order to get y by itself, I had to take the arc sine of both sides. And I'm left with the inverse of sine of x is the arc sine of x. And I would say that this is my inverse. Okay, this is my inverse. So going back to our example that we were just looking at, okay, I'm going to follow the same steps I did to find the inverse of sine x. Okay, I'm going to go ahead and revert back to 8th grade, call it y. Oops. Okay, then I'm going to flip. Okay, then I'm going to solve. So what I'm going to have to do here, obviously, I'm going to subtract 8 from both sides. Then I'm going to divide both sides by negative 3. Okay, and there's 2 ways to go about this. Okay, if I wanted to, I could go ahead and say that it's just this, negative x minus 8 over 3. Or I could do this, because a positive divided by a negative would be this, right? And then from there, I can distribute the minus. So that's going to give me negative x plus 8 over 3. But for all intents and purposes, either one of these would suffice. Okay, so let's look at our second example. So now I've got g of x, and I'm going to follow this same little process. And now my dog is barking bloody murder in the middle of a math video. That's perfect. Let me go see what she's trying to kill. Okay, so now that my dog is calm, let's go ahead and look at this second example. Okay, so still got the eraser. So we've got g of x equals 1/4 times x plus 12, all grouped together. Now, there's two ways to go about this. Well, let's go ahead and revert. So let's revert back to 8th grade. This is y, 1/4 x plus 12. Okay, do the flipperoo. Oops. Okay, so there's two ways to go about this. You can go ahead and distribute the, what do you call it? You can distribute the 1/4, or you can work smart and not hard, which is what I'm going to do, and go ahead and just multiply both sides of the equation by 4. Okay, and what that's going to do, 4 times 1/4, those are inverses. Okay, that's the same thing as times 4 divided by 4. So that's going to give me 4x on the left, and that's going to give me just y plus 12 on the right. Okay, and it's just that simple. And we actually did this I want to say in 1-1 when we were solving an equation. Anyhow, so now I'm going to subtract 12 from both sides. So 4x minus 12 equals y. Okay, and then I'm going to go ahead and say that y is now f inverse of x is equal to 4x minus 12. So that is my inverse. Okay, so now let's look at number 3. Okay, and while I'm erasing, it's important that we use that notation, that just f to the -1, right? Again, we need to get used to seeing that because it's going to be assumed that we know what that means. Okay, so now I've got h of x equals 2/3 x minus 5. Okay, revert. So this is y equals 2/3 x minus 5. Do the flipperoo. H equals 2/3 y minus 5. And now I'm going to solve for y, which is essentially, again, solving for my f inverse of x. Okay, in this case, it wouldn't be f inverse. I'm an idiot. It would be h inverse of x. No. Okay, so what I'm going to do first, add 5 to both sides. Okay, then how do I get rid of this? Well, you could say, oh, you just got to divide by 2/3. Yeah, but that sucks. What does that even mean? The simplest way to look at this, okay, the simplest way to look at this is division is the multiplication of the reciprocal, right? So 2/3, right? The inverse of multiplying by 2/3 is multiplying by the reciprocal of 2/3, 3/2, and watch what's going to happen. 3 times 2 is 6, 3 times 2 is 6, 6/6 is 1, right? So basically, times 3 divided by 3, times 2 divided by 2. It cancels out, leaving me with just y on the right. But this is algebra. What I do to one side, I do to the other. Okay, and I'm going to go ahead and distribute just so it's in y equals mx plus b. So that's going to be 3/2 x plus 5. So h inverse of x, and I'm calling it h inverse of x because the original function was h of x. Okay, I kind of forgot to do that. I think I said f on number 2, but whatever, it should have been g, right? But it doesn't really matter. It's just a name, okay? Anyway, so h inverse of x equals 3/2 x plus 5, and that would be my inverse to h of x, okay? Okay, so let's do one last example, and I'm running out of colors here. I'll use orange because, you know, why not? So this last example is going to be, you know, not much more difficult than the others before it. So we're here on number 4. So I've got j of x equals 3x minus 2 over 6. Okay, so first thing I want to do is revert. So I'm going to call this y, 3x minus 2 over 6. Flipperoo, x equals 3y minus 2 over 6. Okay, now I'm working to get y by itself, okay? So first thing I want to do, I want to make that 6 go away. And the way I'm going to make it go away is doing the inverse of dividing by 6, which is times 6. Those are going to cancel. What I do to one side, I do to the other. So this becomes 6x equals 3y minus 2. Add 2 to both sides, 6x plus 2 equals 3y. And I'm going to divide both sides by 3. 6x plus 2 all over 3 equals y. And again, we want the actual function notation. So this would be j inverse of x. Okay, and if I wanted this in y equals mx plus b, I would say j inverse of x is equal to, I would just divide both of these terms by 3, or put them over 3. So I would have 6x over 3 plus 2 over 3, which gives me j inverse of x is equal to 2x, right? Because 6 over 3 is 2, plus 2/3. Y equals mx plus b. Okay, so now we've got some real world implications going on here. So some lady, Mariana's average running speed is 6 miles per hour. Okay, so step 1, we're being asked to write a function, d of t, that gives the distance in miles as a function of t minutes. Okay, so distance, oh God, distance as a function of t in minutes is equal to 6 miles per hour. So we would have to say 6 times 60, right? Because we're saying 6 miles per hour because we're doing t in minutes. Okay, so 6 miles per hour. Actually, that would be over. Here, let me back up. Okay, so I'm going to want to do a unit conversion before I do this because I've got 6 miles per hour, right? And you should be learning about this in chemistry, or you probably have already, but if not, we'll go over it if we need to in class. But 6 miles per hour, okay, times 1 hour per 60 minutes, okay? And what's going to happen is your hours are going to quote unquote cancel, and you're left with 6 miles per 60 minutes, right? And you're basically just going to divide 6 by 60. Let me grab my calculator here because I'm having a brain fart. And that's going to give you 0.1 miles per 1 minute. So 0.1 miles per minute. So that's our rate of change for the function. So we're just going to say 0.1 times t minutes. Okay, so that's literally our function right there. Okay, so moving on to number 2, what are the units of the domain and range of d of t? So the units of our domain, the units of t are simply minutes, right? And we can go ahead, instead of saying 0.1, let's go ahead and just say 1/10 t. I like that better because you guys know I like fractions. Fractions are just easier to work with. So what we've basically got, if we're saying 1 over 10, we're saying 1 mile, well, mile, not plural, 1 mile per 10 minutes, which is pretty dang good. Dang, that lady can move. Well, that's not that good. It's better than me. Anyway, so that would be the units of our domain. It's in minutes. And the units of our range. The units of our range are in miles. Pretty straightforward. Pretty straightforward. So the domain and range in both interval and parenthetical notation. So the domain, what is our domain restriction? Well, we can't have negative time, right? So we're going to say that t is greater than or equal to 0. So if we're using parenthetical notation, we're going to say 0, and we're going to include with the square bracket onto positive infinity, right? And if we're using set notation, we would say that we have t such that t is a real number, hopefully, and our domain restriction would simply be that t is greater than or equal to 0. So these would be our two answers for our domain. Let's do our range in a different color. And if you're still having trouble with all this notation, as far as like interval notation in general, again, ask as many questions as you can. So continuing on into our range. So what is our range, right? So also, our range is also going to be such that d is greater than or equal to 0. D is our distance, right? And if I want to be really, really nitpicky about this, I would say d of t. I should go ahead and do that. Practice what I preach. So d of t is greater than or equal to 0. And if we're using set notation, d of t such that d is a real number, and our restriction again is d of t is greater than or equal to 0. See if I can't even make that fit. So I'm just going to abbreviate and say it's d. Okay, and our notation would look the same. Okay, so our domain and range are pretty much the exact same thing. They're starting at 0 and moving on into positive infinity. So what are the units of the domain and range of the distance function's inverse, d inverse of t? So first of all, we need to calculate, well, what is the function's inverse? Okay, so if d of t equals 1/10 t, what we need to do is revert, right? So we're just going to call it d equals 1/10 t, and then we're going to do the old flipperoo and say that this is t equals 1/10 of t. Oh my goodness, I can't talk. 1/10 of d. Okay, so what I'm going to do from here, I'm going to multiply both sides by 10, because the inverse of multiplying 1 over 10 is multiplying its inverse, 10 over 1. And what I do to one side, I do to the other. So I have 10t equals, these are inverses. So what I end up with, d inverse of t equals 10 times the number of minutes. Okay, so write the domain and range of the inverse function in both interval notation and set notation. Okay, so what is my domain and range this time? Well, turns out my domain and range is going to be exactly the same. It's going to be exactly the same. Okay, so I'm not even going to bother going about that. How many miles will it take Mariana to run 2.5, or sorry, how many minutes will it take Mariana to run 2.5 miles? So we really, really have to think here, because our function was distance as a function of time, right? Distance is a function of time. Well, now we're given a distance. So this inverse function, what I've really found is that I have found time as a function of distance, okay? And you can see, so the inverse of this guy, d of t, would be t of d. So distance as a function of time, its inverse is time as a function of distance. Okay, so what I'll end up with, if I left this switched the way I did right here, if I just kept saying t equals 1/10 the distance, or times the distance, right? And I was solving, okay? So basically, if I left my variable switch, I would have that t as a function of distance is equal to 10 times the distance. So for example, if we look here back to our rate of change, 1 mile per 10 minutes. Well, the inverse of that would be 10 minutes for every 1 mile. That's what we're getting at. Okay, this would be our inverse rate of change, which is obvious right here. Okay, if I rewrite 10d into rise over run, delta y over delta x, right? I would have 10 minutes per 1 mile times the distance. Okay, and we're told the distance in this case is 2.5. So I would just say 10 times 2.5, and that's going to give me 25. So it's going to take her 25 minutes to run 2.5 miles. Okay, and if that made your brain hurt, be sure and ask me some questions about that, because you're going to need to understand that one. Okay, so here we have some algebraic proof as to whether or not two functions are inverses. So we saw geometric proof here, right, when they have symmetry about the line y equals x. Okay, algebraically speaking, we can tell if two functions are inverses, basically, if we get, and I'm writing this backwards, if we have f of f inverse of x equal to x. If this is true, then those two functions are in fact inverses. Okay, so let's try that. So we are told, well, we were supposed to be told that f and f inverse, obviously, they're inverses. Now, if that's the case, let's see what f of f inverse of x is. Okay, so again, what does that mean? That means I'm taking f inverse, right? This is going back to composition of functions. I'm going to take f inverse, this guy right here that I just circled, and I'm going to plug it in for every instance of x in f. So instead of 2x minus 4, I'm going to have 2f inverse of x minus 4. And what that amounts to is 2 times the actual function, so x plus 4 all over 2. And then I still have to do the minus 4. Okay, so what I'm going to do next, well, you can see right here, I'm multiplying by 2 and I'm also dividing by 2. Okay, those two are inverses. That's gone. Okay, so what I'm left with is x plus 4 minus 4. And again, we have plus 4 minus 4. That's just going to give me 0. And I'm left with x, meaning that f of f inverse of x is equal to x. If it's true, then they're inverses. And clearly we see that it is true. So these two functions here, f and f to the minus 1, are in fact inverses. Okay, so let's see how this works here. So let's find the inverses and then prove using composition of functions, using algebra, that they are so. So f of x equals 4x minus 14. So I'm going to revert and say that this is y equals 4x minus 14. I'm going to do the flipperoo. X equals 4y minus 14. You can bring that up here. So I'm going to add 14 to both sides. So x plus 14 equals 4y. And I'm going to divide by 4 on both sides. So I'm going to have x plus 14 all over 4 equals my f inverse of x. Now, how am I going to prove that they're inverses? Again, that goes back to this here. So I'm going to use composition of functions. So f of f inverse, I'm going to plug in f inverse here for x into f, right? So instead of 4x minus 14, it becomes 4f inverse minus 14. Okay, so the 4 being multiplied and the 4 being divided by, okay, they're inverses, those cancel. That's going to leave me with x plus 14 minus 14. 14 minus 14 will give me 0. And guess what? There's my proof, okay, that this and this are inverses. Okay, one more example. Let me erase and give myself some room. Okay, and I'm going to use pink this time. So I'm here looking at number 2. So g of x equals 1/2 x plus 3. So I'm going to revert, call this guy y again. And then I'm going to flip x equals 1/2 y plus 3. Okay, add 3 to, or sorry, subtract 3 from both sides. So I'm going to have x minus 3 equals 1/2 y. Okay, the inverse of multiplying by 1 over 2 is multiplying by the reciprocal of 1 over 2, which is multiplying by 2. So those are gone. What I do to one side, I do to the other. I'm going to go ahead and distribute just for funsies. So 2x minus 6 equals my inverse of g, so my g inverse of x, right, because it's called g. Okay, now I'm going to use algebra to prove, and by algebra I mean composition, to prove that they are in fact inverses. So I'm going to say g of g inverse x is equal to 1/2 x. Instead of 1/2 x, it's going to be g inverse, so 1/2 of 2x minus 6, and then that plus 3. So I'm going to go ahead and distribute. So 1/2 times 2x, 1/2 times negative 6, so 1/2 times 2x, that's just going to give me x, and 1/2 times negative 3, or negative 6, that's going to give me negative 3, and minus 3 plus 3, I'm left with g of g inverse of x is equal to x, and thus this guy and this guy are proven to be inverses. So here's another look at our EQs, and we answered every one of those. If there's any questions over any of this in the video, please let me know, and obviously ask a crap ton of questions when you're working on the do now and the lesson practice itself. All right, kiddos, that's all I got on this video. Goodbye.